So far in our investigation of the crust beneath Scotland, we've established that there are three main layers in the crust, and that the upper 6 kilometre per second layer is made up of Caledonian metamorphosed sediments. This rock consists mainly of quartz and felspar, and so it's silica rich. The layer also contains radioactive isotopes of potassium, thorium and uranium in concentrations that average for the continental crust. Now we're faced with the problem of finding out about the rocks which make up other layers in the crust. The 6.4 kilometre per second layer is 8 to 12 kilometres beneath the surface at the Lisp line. As it's beneath the Caledonian layer, it's likely to be older. So if this layer has been brought up to the surface elsewhere, its age will give us a clue to its identity. Here's the Caledonian layer, which was metamorphosed some 450 million years ago. But up here, in the northwest coast of Scotland, is an area of rock which was considerably older. These rocks are called the Lewisian, after the Isle of Lewis, where they are particularly abundant. So the age of the Lewisian makes it a promising candidate, but we need some evidence that it connects with the 6.4 kilometre per second layer underlying the Caledonian layer. There's another seismic method that can tell us this, seismic reflection. This uses sound waves that travel almost vertically in the crust, unlike in refraction where they travel almost horizontally. These waves travelling down through the crust are reflected back to the surface at rock interfaces. By recording the arrival times of these reflected waves back at the surface, we can build up a profile of the crust which shows how it changes horizontally in much greater detail than we can by the refraction method. A seismic reflection profile was shot across here at sea, and here's the structure it revealed. Beneath the top 2 to 3 kilometres, the reflectors all dip down towards the right, that's towards the southeast, and they extend about 12 kilometres beneath the surface. The strong set of reflectors from the centre to the right of the profile are the Caledonian layer. Beneath this, and extending to the west, there's another set of reflectors which have been identified as the Lewisian layer. We know this because it outcrops at a small island called Stack Skerry, and the rock here is Lewisian. So let's see what Steve was able to find over in the northwest, here by Loch Assynt.
This mountain is made out of a tremendous thickness of sediments, and the step-like features are bedding. And the dip is quite gentle down to the east. And you've probably seen these sediments at summer school. They're coarse sandstones, coarse feldspathic sandstones. They're about the same age as the material at Melness, but these haven't been metamorphosed. So they're equivalent to the Caledonian layer. And to see the higher velocity material, we'll have to go down a bit. Here's the boundary, and here are the Caledonian rocks. And this is what we're after. Well, it's banded, pretty vaguely banded, but the banding is quite steep. So the boundary is an unconformity. And these rocks are very much older than the Caledonian rocks above, about 2,000 million years older. This is a pretty miserable little outcrop, and to see things better, we'll have to go to the west. And there, we've got some absolutely tremendous outcrops. Right the way up the northwest coast, virtually all trace of the Caledonian sediments has been stripped off by glaciation, just a few erosional remnants left. And even the scenery is totally different. There's rock everywhere. There aren't any weaknesses like bedding to form neat ledges and bands, and the whole appearance is what you might call knobbly. But where you've got fresh exposures, you can see that this layer is pretty complicated. For a start, it's got quite a variation in colour of rock type. It's horribly contorted, so it's a mixture of rock types. And when you have something with a lot of folds in it, you can say that it's had quite a long history. And this is the commonest rock type. It's quite pale. It's quite coarse, it's crystalline, and the crystals all interlock. And it's banded. It's a metamorphic rock, and you've met it before, it's a gneiss. There's plenty of quartz, so it's silica-rich. And there's plagioclase feldspar, so that means quite high aluminium, sodium, and calcium. But there are some other minerals in there, and they're the most interesting ones. They're dark, and they're iron and magnesium rich. They're pyroxenes, and they don't contain any water, so the whole rock is anhydrous. It's a granulite facies. So how did these rocks get into this state? For a start, it's been around for nearly 3,000 million years. And at some stage, it was about 40 kilometers down, and it suffered regional metamorphism, which meant high temperatures and high pressures. And that's why it's so dry. The water's been driven off. These numbers are nowhere near as high as they were at Melness from the Caledonian layer. In fact, the heat-producing elements are almost at the limits of detection of this instrument. In other words, potassium, uranium, and thorium are depleted in this gneiss. There's no way this layer can heat up now, but it was hot once. But that drove the water off, and the water carried off the heat-producing elements. So, this is a piece of crust that died, and it's lain in state for a considerable period of time.
So the Lewisian is our next layer down in the crust. The rock's granulite gneiss, and like the metamorphosed sediments above, it's silica-rich. But unlike the Caledonian layer, the Lewisian contains a lot of the ferromagnesium mineral pyroxene, and it's lost the radioactive elements. Well, these two layers of the crust account for most of the surface geology of Scotland, apart from these thin layers of low-velocity rock and these surface lavas. The only other major rock type at the surface are these red areas, which are dotted all over the highlands. One of the largest of these is here in the Cairngorm Mountains.
Well, these are the hottest rocks in Scotland, and they're very rich in uranium and thorium, as well as potassium. But what's pretty obvious is that they're not metamorphosed sediments. This is about the best example of a granite you could hope to find. And if you take a close look, you can see that it's very coarse, it's crystalline, the grains all interlock, and they're random. Perfect igneous texture. And the minerals you can see are quartz, greasy grey, feldspar, which is pink, and there's some little flecks of black mica. So, a granite. And there's plenty of it. And this granite formed one of the last crust-forming events in this area. And somehow it mopped up uranium, thorium, and potassium from the rest of the crust, and was the last stage in the refining process which extracts continental crust from the mantle. It formed about 8 kilometers down, so quite clearly there's been a tremendous amount of erosion. But since the granites are much harder than the surrounding rocks, they stand out as the huge Cairngorms Massif. But just because the granites are tough doesn't mean to say that they aren't weathered. These tores bear witness to the fact that they certainly are. What happens is that the cracks get filled with water. At these altitudes, water will freeze quite often in the year. And as water freezes, it expands and it wedges off large blocks. The two main minerals in the rock, quartz and feldspar, have different thermal expansions. And so with all the heating up and cooling down that goes on, they tend to separate from one another. And eventually, the rock becomes very, very crumbly. And the end product is a gravel composed out of the two main minerals, quartz and feldspar, although there are bits of mica floating around in it as well. Of the three main minerals, only quartz is resistant to chemical attack. The other two, feldspars and micas, break down, and they form two components. On the one hand, they break down to clay minerals, and on the other, elements like potassium enter into solution. And some of the uranium gets into solution as well, and away it goes, along with the quartz grains, clay minerals and so on. And large old granite masses like the cairngorms form the parents for younger sediments.
The cairngorm granites appear extremely large when you're standing on them, but they don't show up on the list profile, which passes right through them. So how are we going to find out how far they extend beneath the surface? The granite and the surrounding Caledonian metamorphosed sediments are very different rocks. They have different densities. Granite is less dense. The geophysical technique that measures density is gravity. This gravity map of the cairngorms area shows gravity anomalies, Bouguer anomalies. The positive anomalies are coloured red and the negative ones blue. The negative anomalies correspond well with the granite outcrops. The granite is less dense than the surrounding rocks, so produces a negative anomaly. From the shape and value of the anomaly, it's possible to calculate the extent of the granite. The cairngorm granite extends to about 12 kilometres below the surface, and this is how it would look in the cross-section of the crust. It's only in the upper layer of the crust. So far, we've found two layers of the crust. This upper layer, composed of metamorphosed sediments and granites of Caledonian age, and this middle layer of very old granulite gneiss. This bottom layer of the crust doesn't outcrop at the surface. So first let's see what this thin, low-velocity layer in the Midland Valley is made of. Steve has gone here to Ely, on the northern shore of the Firth of Forth, where there's a good outcrop of this low-velocity rock.
Everything's different here. The P-wave velocity is different, the scenery is different, even the weather's taken a change for the better, and the rocks look different too. They're quite soft and crumbly, and they've got nice rounded grains in them. If that's not enough to convince you, in this unit, up here, there's a beautiful river channel. Comes down through here. Above it, there's a siltstone, shaly siltstone, and about 2 meters above that, there's a coal seam. They're sedimentary rocks, and not very much altered ones at that. And they're about 100 million years younger than the metamorphic rocks and granites of the highlands. So, the sediments, what sort of grains do they have in them? Well, it's fine-grained. Nearly all the grains are quartz, although there is a little bit of mica in there, black mica, but there are no feldspars. It's almost certain that these grains were eroded away from the highlands, transported here. They're inherited from the Caledonian layer. That's not the only inherited thing about these rocks. I've just done a rapid gamma ray survey, and though the sandstones aren't very radioactive, the more organic rich rocks, like the shaly siltstone, and particularly the coal, are radioactive. In fact, the coal contains about 6 parts per million of uranium. Somehow the organic rich sediments were able to extract uranium from the ancient river waters that poured off the highlands to create a second kind of enrichment of heat-producing elements in this upper sedimentary layer of the crust. And if this layer were ever deeply buried, it would begin to heat itself up, metamorphose itself, and may even get to the stage of melting.
This low-velocity layer is made up of sediments like those we saw at Ely. But the surface geology shows us that some of the sediments in the Midland Valley are a bit older than the Carboniferous age sediments at Ely. These are up to 400 million years old, Devonian in age, but still unmetamorphosed. The thin, low-velocity sediments in this area around the Moray Firth are also of Devonian age. But although these sediments are underlain by the Caledonian layer, the Midland Valley sediments are not. The Caledonian layer stops at the Highland boundary fault and is replaced by a layer with a velocity just below 6 kilometres per second. This layer comes to the surface in the southern uplands, and from these rocks we know that the layer is 400 to 500 million years old, so it is of similar age to the Caledonian. So there are younger sediments above and older Lewisian rocks below. The crust does get older with depth. But we still have no information about the deepest crustal layer, the 7 kilometre per second layer, and we only have the velocity of 8 kilometres per second to support my assertion that the layer beneath it is prototype mantle.
No amount of tilting and erosion has been able to get the deep crust and the mantle to the surface. But there are geological processes that can. Not long after these sediments were deposited, a whole series of volcanoes punched their way through them, and they brought dark basaltic magma to the surface. You can see the remnants of these younger volcanoes all the way along this part of the Fifeshire coast. Basalts only form by melting of the mantle, and to form volcanoes they have to squeeze their way right through the lithosphere, and if they're violent enough they can bring chunks of it up to the surface. And I'm hoping that in this volcanic debris we can find lumps of the deep layers that we're looking for. There's no point just sitting back and admiring these lumps. Let's take a look inside. It's got black phenocrysts in it, set in a fine-grained ground mass. It's just a common garden porphyritic basalt. And that's hardly surprising. Most of the samples here came from just beneath the volcano, from slightly older lavas and sediments. What we really need to find is a mineral which we know crystallized at the pressures that go together with the depths that we're interested in. And there are quite a few mineral fragments in here. I can see quite a lot of biotite, and there's a red mineral there, which is very interesting. It's a garnet. Well, that clinches it. This is the place to look for bits of the crust and mantle. And I did have a look a little earlier, and I found one piece which is pale, coarsely crystalline, and I think it's a piece of the lower crust. But it needs an awful lot of experience and a certain amount of luck to to come up with a real McCoy, because there's such a tremendous variety of nodules in this material, different shapes, different colours, different sizes. You'd have to collect a comprehensive suite of the nodules, take them back to the lab, cut them up, look at them through a microscope, analyse the minerals and so on. Fortunately, a team of geologists from Edinburgh University have done the spade work for us. This one is full of garnets. It's a garnet granulite, and it comes from the lower crust. And the fragments in this one are even more interesting. They're periddotites, and they're from the upper mantle beneath this part of Scotland. So, these are samples of the deep crust and the upper mantle. We've completed our cross-section through the Scottish lithosphere.
So let's summarise what we've found out about the crust beneath Scotland. Nodules from the volcanic vent agglomerate support the idea that this 8 km per second layer is periddotite, the upper mantle, and suggest the 7 km per second layer, the lowest layer in the crust, has a composition akin to garnet granulite. The 6.4 km per second layer is old Lewisian granulite gneiss, which is depleted of heat-producing elements. The upper layer, with a velocity of around 6, is made up mainly of metamorphosed sediments with an average concentration of heat-producing elements, and granites with high concentrations of heat-producing elements. Finally, there are thin layers of sediments with velocities less than 5 km per second and containing layers of organic rich rocks with high concentrations of the heat-producing elements. But the LISP survey extends south of the Southern Uplands Fault down into England. Let's see what it shows. It's a very different and somewhat confused picture, and we don't have time to go into it, but clearly the Southern Uplands Fault represents a major change in the crust. We think that the reason for this change is that the crust of Scotland and the crust of England were formed in different places and so had a different history. They were far apart on opposite sides of an old ocean which existed long before the present Atlantic Ocean began to open up. The Scottish continental crust and the English continental crust were brought together when this earlier ocean began to shrink, being subducted along one edge. There was igneous activity at this destructive plate margin, producing basaltic rocks like those we saw in the volcanic vents at Ely. Finally, the ocean closed completely, and England and Scotland were joined.